Today's presenter is Hilda Pata. She's located in our Crawley, UK office. She has a master's in integrated reservoir management from the University Central de Venezuela. She also has extensive knowledge of well and seismic data management in multi-platform environments, and she brings with her more than 27 years in the industry. So I just wanted to tell everybody this is a brief overview of one of our advanced interpretation technologies. I wanted to give you an overview of how to visualize and interpret subsurface data so you can guide your drilling plans. I think the beautiful part about Inside Earth is that you can image and interpret in hours or days instead of months. So this gives you more time to evaluate plays and validate your findings. Also, just so you know, these compute-intensive workflows also perform seamlessly in the cloud. So with that, I'll hand it over to Hilda.
Thank you, Jasmine. Good morning, good evening, good afternoon to everyone. We are ready to start then the webinar today. We have at the moment just a small overview about the GeoSoftware portfolio, just to let you know that we are part of a bigger suite of applications, and one of the applications that we are working today is with Inside Earth, and we have also Hampton Russell JSON Power Log model and Velpro. So we are going to focus today in Inside Earth. Inside Earth is our advanced 3D visualization interpretation, and we will see in the next slides a little bit of detail of that and an overview. For today, we are going to talk about a brief introduction about Inside Earth, solid body interpretation, and fault interpretation techniques. Inside Earth is the software that we are using to do the interpretation in 3D. We can do a structural and stratigraphic interpretation. We have some tools for data conditioning in order to manage better our algorithm for the interpretation task. We have a fracture network tool, and we have a well planning module as well. You can see here a 3D view and all the elements that we can create in our software. The modules that we are using in Inside Earth are imaging. It's just to data management and loading and create the framework, the project to work in. We have the FaultSpark. We have the FaultFractureSpark, PaleoSpark, and WellPath. All those modules are just included in the different licensing, different words to start with. Today we are going to focus on FaultSpark and FaultFractureSpark. Before starting, this is only to let you know for people that haven't seen that before. This is an overview about the user interface. You can see in the left part of the window or the data list, you can just see exactly what you have in your project at the moment. In the middle top, you have the process networks. Every different process that you are running, you will see this in a small box in here. And every time that you are selecting one of these process networks, you will see the parameters associated with at the bottom. And of course, the 3D display, and then you can QC what you are doing. In FaultSpark, we can quickly identify different kind of solid structures. As you can see in this example, we have some domes, pillows, and some massif. And we can just create the closed 3D geobody with many different kind of data sets. And we can reduce the time for the interpretation of all these different elements. In FaultFractureSpark, this is the model that we are using to identify and interpret the fault architecture that we have in our data. It's a very quick and accurate way to generate the fault planes. Just with a few steps, we can create the accurate fault plane for that. And this is one visualization or general visualization that what we are having after finishing the workflow. Let's go and talk about a little bit about the data set that we are using today. This is a small volume that we have in this area in Louisiana, in Eugene Island. And we are using this small data set just to show you how to use the soil interpretation and FaultFractureSpark. We are offering this workflow in all our processes. We are just based on first our interpretation in a very good quality data. To do that, we are applying first the noise removal processes. Then we are calculating different attributes. In this example, we have the horizon edge stack attribute that we are using for many of our processes inside Earth. And finally is using this advanced fault imaging to generate the volume with the fault probability, and then use that to generate further the fault planes. Before starting anything, this could be in soil interpretation, in fault interpretation on paleo, which is out of the scope today, we have to apply first the data conditioning processes, because we need to remove the noise that we don't see, but the software and the algorithm can detect. And perhaps we are getting a response that is not properly the event that we are looking for. So it will improve the quality of the data set and improve the image quality and all the features that we are identifying in our different processes. I would like to show this slide that is explained very well why it's important to just spend a little bit of time before starting any of the processes, because we have in this is an example of the spectrum, the complete spectrum. We can see that we have all along fault, fracture, noise, and horizon. We have in this spectrum with the discontinuities represent the left part of the histogram, and the continuous element are the right-hand side. But you can see that all over the fault fractures, we have noise. And this is the noise that we have to remove. But we have to be careful as well, because we need to avoid to over-conditioning the data, because sometimes we are removing important features that we should keep on the data set. So it's kind of a tool that is helping us to improve the quality, but at the same time, we will have to be very careful when we are applying that to avoid removing important things. The first thing that we have to do in this example, we have done the small volume here. You can see that we have some feature and hat. This is the salt body that we are going to interpret later on, and we can just roughly identify that. Well, we have to check first our volume. In this case, if we have to mute some the volume, if we have to apply some the trace to just improve the final data that we are going to use in the processes. We have to then start scrolling through the volume and then see if we have some acquisition footprint, and we can detect the size and the orientation of that. A good thing that Inside Earth allows you to data condition in 3 different orientations, not only inline and cross-line, but also in oblique orientation. So then we on our Reconnaissance, we can just then check the data and see where are the features that we want to capture from the data set. In here, we see, well, some important major faults and where the soil body potentially will be. So we are familiar then with the data set. This is an example of the effect of after applying some of the tools that we have for footprint removal. You can see before the original data and after applying some of the tool of data conditioning, and we are improving our data. Okay, just to let you know that we have a very clever way to play with in the data conditioning, because in this batch footprint removal process, we can do several data conditioning operations in one go. We can do that adding a new iteration and then set up different cross-line, different inline, different oblique orientation, and then run one unique process, and at the end, we will get one horizon orientation volume as a result of that, and of course, the volume data conditioning. Okay. Regarding this horizon orientation, let's talk about a little bit of that. This is the first attribute that we are getting that in the first process, and we will take advantage of this horizon orientation attribute just to use that in the next steps to interpret our solve body. What we have in the horizon orientation volume, this is a 3-component vector volume, and as you can see here, we have 3 different views. This is selecting the display in the X direction, Y direction, Z direction. As you can see how different it is. It's the same volume, and we can extract different orientation from that. And even better, we can apply one operation on it and then split this horizon orientation in a dip volume and a strike volume. It's just playing with different attributes. Now, let's go and see how we can use that in our next process, which is going to be the salt interpretation. What we are doing here in the next steps is going to be on the solid body imaging, apply some volume attributes, use one technique that we call mesh painter, and finally refining that mesh using the surface graphing. And at the end, we will have our solid body automatically generated. Let's see how it works. In interpretation workflow, as usual, data condition the data, go for salt interpretation, fault interpretation, and finally horizon interpretation. Why? Because we can use this geobody as a constraint to interpret and generate the fault planes, and also use both of them as a constraint to interpret the horizon. What we have in here, data condition, salt interpretation, fault interpretation, horizon interpretation, we are going to focus now in the salt. What we have in here, some notes about that. Salt body becoming variant shapes, and if you remember at the beginning of the presentation, we can interpret different kind of salt bodies, domes, massive. Then it doesn't matter which one, what kind of chain it can. We can apply the same technique of them, and finally get the geobody created. The objective here is just to image the salt sediment interface in the seismic volume, and to do that, we will use some attributes, apply some quick techniques, and finally get this salt sediment interface. And the workflow here is based on voxel properties. That's why we will be using mainly a combination of the visual display in the 3D display and histograms. We will use that as a constraint to generate and apply the algorithm. Data condition, examine ourselves, generate some attributes, and finally create the surface graphing. We are creating in the one volume called horizon orientation, and we are splitting that in the dip and strike, and then we will use this dip attribute to try to see exactly where the boundaries are. Before going further, this is only to mention that inside Earth we have a co-rendering techniques, and this is very useful because it allows you to display up to 4 different volumes at the same time with different color bars, and then you can, using the co-render, display different attributes and see where the contrast in between. In this example, we have the amplitude volume, we have the fall enhance, and you can see the fault in light green. We have also the deep volume and the horizon edge stat, which is another attribute that we calculate here to create this fault interpretation techniques. In co-rendering, this is in our data set, the co-rendering of the amplitude volume and the deep volume. So this is the first indication that, in fact, my soul body should be in some way in that position. I would like to capture the boundary between this soul body and my sediments. Going here, you can see that we have some stability horizon going up, and not always is easy just to get exactly the boundary of those horizons with the soul body. So let's go and calculate that automatically. What we are using is the surface wrapping techniques, and one of the tools that we have is the mesh painter. In here we have the display in time orientation. The volume that is displaying here is the horizon orientation, and with the kind of color bar that we have, the soul body is represented by the red color in here. So the way to do that is just play with the sliders in this part, and then set up the min and max, and then with the central bar you can scroll and QC and check going through the volume if you are capturing the soul interface. Then we change the orientation because we need to QC in different orientation our volume. This is the example doing the same thing in lines. We have the histogram, which is a very useful tool that we are using to do our work here. And you can play with the sliders in the histogram in there. You can play with the sliders in here, and you can QC going through the horizon, the volume using this slider. And in the orientation, the line orientation, we can see that we are capturing more or less the boundary sediments in here. And finally, we have the view for the cross line. And then in this example, we need just to set up the target more or less between 60 and 90 in here. And this is the result of looking at this mesh painter and looking at the adjustment with the slide bars in the histogram. Okay, after adjusting our boundaries in there, the target value, we need just to select an option to paint the target voxel. The software will paint everything that we are telling to identify in between these target values. And this is an example after applying the calculation. You can see in the different orientation here in inline, cross line, and time. And what we see in gray, to me is gray. I don't know, depending on your resolution, what color are you looking at, but this light color here is exactly the capture with the mesh painter. So the next steps is just build the paint mesh, and after finishing this process, we are creating something like this. It's just building the mesh using the different constraints that we applying before, and automatically the software will create this soul body. This is the display with the amplitudes co-rendered with the horizon orientation, and the resulting soul body automatically created with just a few clicks in this picture. However, we have in this part, this is one of the methods. We have many ways to calculate the soul. We can apply different attributes. I have applied in here only the horizon orientation attribute. We have many other. We can apply the eigenvalues, etc. And we can see in our data set which one is the attribute to better suit with our seismic response. In this workflow, we were using only horizon orientation. This is another way to do the same thing that we were doing with the soul interpretation, but in this case, if you want even to have more control about your process, you can do it in a kind of semi-automatic way. And using the same mesh painter, you will see the same display. Red is the salt body. You see that the slider is a little bit small. What you have to do in here is just paint the border of your salt boundary and then fill that, and it will fill in that level. And then you need to go back in the slider and move a little bit and repeat the process. After several iterations and doing that paintbrush and fill the image of the salt in there, when you finish the whole range, you will see that in different processes. And you can, at the end, see roughly in different kind of depths, different steps that you were manually painting and filling and creating. And when you click on the Build Paint Mesh, it will do the same process to create that. But in this case, we have even more another very useful tool that is playing with the wrapping steps. As you can see here, applying 20, 40, 60, and finally with 100. So this wrapping step is helping us to go from a very rough connection between different depths of our interpretation and smoothing the geobody and finally getting the image all connected and all smooth. So this is the second way to interpret the salt body. So one is only few clicks, and the second one you can also get a little bit more of control and of course doing step by step. Then after creating this mesh, the next question would be, what can I do with that? Well, we can use this mesh from the data list. We can just right click and export that as a GoCAD object, a multi-set for another software. We have another option to convert the mesh into point set and export in ASCII. And we can create a discrete volume and export this volume in as a CY. This volume will contain one value inside, a constant value inside the salt body, and another values outside. It can be 0, 1. And then if you want to export this CY file to other software, we can do it in different formats. As you can see, a short visualization that we have for the exporting format, we can do in the CY, Seismic Data Paradigm, SMT. Okay. After the salt interpretation, let's go then and do the next part, which is the fault extraction. And the structural interpretation is using exactly the same focus, but now we did the salt interpretation, we are going to do next the fault interpretation. What we are doing in here in the next part is just calculating the edge stack, applying some fault imaging attributes, create the fault cuts, and generate the fault planes. And this is an example that what we have at the end. Okay, as usual, we have to start with the noise removal. In this case, it's not necessary because we already did that to apply the salt interpretation. Then calculate the horizon edge stack volume. And we will use this volume just as an input for the next part, which is the advanced fault imaging, and create the fault enhanced volume. In the fault imaging result, after calculating this horizon attribute, this is called the horizon edge stack. It's one of the core attributes that we use in InsideEarth. We will use that as an input for the fault imaging task, and then it will create the strike enhanced volume. It will apply some processes in between and generate the deep enhanced volume, another process, and finally it will create the fault enhanced volume. And what it's doing here, every time, every single step between one volume and the next is applying the refinement using the window random transform. And what it's doing is filtering and removing noise in every steps. You can see from the horizon stack and how these images are cleaner and cleaner. Then, after generating the fault enhance, we are going to do the fault interpretation. The fault interpretation is starting with 2 volumes generated from the previous process. One is the fault enhance and one is the fault orientation. These volumes are used to extract the fault cuts. You can see in some way some alignments that it could be the fault planes. These fault cuts will be used to apply another process, which is the planar clustering. And finally, we will generate with the planar clustering the fault surfaces. All those volumes are using auto extraction of the fault planes, and everything is controlled by the size that we are using in our voxels and the operators. We have so many parameters to control that and see how accurate are they. And the horizon stack volume that we are using here is one thing that we have to keep in mind, that the horizon stack is showing us in black the discontinuities, and the sediment on the continuous part is in white. And we are using then that to create the opposite scene to generate the fault images. In the advanced fault enhance, we are generating 6 different volumes. Some of them are intermediate. We can just apply few parameters on that. This is only to show you quickly. We are not going into detail on this. That show you quickly that we are going to set up the parameter for strike, deep, and fault enhance. Then this is an image of the result. As you can see, that is the opposite of the horizon stack. The fault enhance now has in white the fault probability. Well, we have this fault enhance created and using that to calculate the fault codes and planar clustering. We are doing that in the extract fault codes. This process, what it's doing is just regrouping the points in planar features, but still they are points. And you can see in here this planar, the points created and forming the ones that it could be in the next step of the fault planes. And then the planar clustering are grouping those alignments from the fault codes and creating the point sets that will be generating the fault planes. The process is for the fault codes is very simple and easy, few parameters, and then run. And this is an output that we have in this process. We can control that with the voxel value. We have to see with the histogram which one is are the numbers that we need to keep, the minimum value that we want to keep on that. And this is the way that we can control how much detail we will get applying this process, okay? Then the fault codes are using to calculate the planar clustering, and then you see that this at this time we have something that is more likely to be a fault plane now. After calculating that, we can see the data using the co-rendering technique. We have the original amplitude volume here. We roughly can see where the fault planes could be. Then using the co-rendering of the amplitude with the fault enhance, you see in light green the faults, and then see how good the software has been running the process. And also you can use the fault plane and clip to this view and use that as a QC as well. We can apply some surface conditioning and then generate the final fault planes. You can do some operation as well. Sometimes you need to merge some of the point sets and create only one fault plane with that, just minor addition. But at the end, you are just creating all those fault planes, and they are ready to export and use in another process or another platform. Finally, this is the result, just applying this small data set just to let you know the way to use salt interpretation and fault interpretation. So this is basically what I wanted to show you today. And then just to let you know some reference that we have for that, some paper from Jeff Dorn, and one of them in company with Joseph Dominguez, and all related with all the techniques that we have been using in here, and all the different algorithms that we are applying are based on this theory in here, and some of the paper with the result and the very good results. Now I'm going to pass to Jasmine, and she will continue with the next part because she is just taking care of the question. Thank you very much for your attention, and let's see what the information that Jasmine has, and we will continue with the questions. Jasmine?
Thanks again for that great presentation, Hilda. And in case you want to get some information right now, you can go to cg.com/InsideEarth for more information. And then cg.com/advantage will also take you to an area where there are videos and links that you can visit right now. But just so you know, as soon as we are finished here, the video will become available, and we will send you additional information as well. Also, feel free to contact us should you have any questions that came up either today or later on. You can reach the presenter directly, hilda.parr@cg.com. Also, gs.solutions@cg.com as well. And with that, we thank you for taking the time to attend today's webinar.